I had sushi. Did you check the homework yesterday? We went to Gourmet House.
Yes.
So perfect.
Thank you.
Oh.
All right. Here we go. Here we go. We got a lot. We got to squeeze. What?
An extra 25 minutes.
110 minutes into 80 today because we got ripped off. Yesterday. Yes. There you go. Now, so where we were, where we're headed with this, and we are. It is more of this today, but the new thing. So for those that were gone, we did add in this idea about sigma notation. Okay, now you did that last year in advanced math. The sigma notation is about adding up. Who was Shelby? You were gone. Anybody else? Did you get a chance to see?
It wouldn't open up on my combo.
Okay. Well, and Anna, right? Okay. Did you get a chance to look at her? Okay. Now, well, it was only partly done anyway, just because of the fire drill. So what we did is we looked at this idea of sigma notation, which just means to add up, add up a series of terms. And so if we go back, so if we go back here to, here's an example. Time for this. Okay. Oh, that's something. All right. So in sigma notation, so what we said, sigma notation has these parts to it. This says I equals 3, and this is the ending point, and it goes by ones. So if I is a 3, we plug a 3 into there, that would be a 9. We plug a 4 into there, that would be a 16. We plug a 5.
We were right. It's up there.
Oh, charger.
Gosh, come on,
All right.
get on that.
So put in a 3, you get 9. Put in a 4, you get 16. Put in a 5, you get 25. Put in a 6, you get 36. And you stop when you get to this point. And then you add them up because sigma stands for sum. Sigma stands for sum. It adds up the terms of the sequence. Now, this particular example, we were showing yesterday that you can start the I at anything you want here. It always goes by ones until you get to this point. The example we were showing here is that you can always make a sigma and rewrite it so it can start wherever you want it to. It doesn't have to start at 1. We like it to start at 1, but it doesn't have to. So this one starts at 3, then goes to 4, then to 5, then to 6. We said that if you just rearrange this formula a little bit, you could get the same thing. If I is a 1, you get 3 squared is 9. If I is a 2, you get 4 squared is 16. If I is a 3, you get 5 squared is 25. And finally, if I is a 4, you get 6 squared, which is 36. These two are identical. And it even looks like kind of a shift. This looks like a left shift of 2, which is kind of what it is. Instead of starting at 3, you start at 1. Okay, was that Kate? Was that kind of what you were?
Yeah, but if you do the reverse order, make it like, if you have like an I minus 1 squared, you make it, bump the I up 1, or with,
Yeah. So,
like number 21.
okay. So on the LH packet here, if we look at number 21 over here. Okay, now, here would be the only downside of this is the directions here were to use the summation formulas, and all the summation formulas start with I being a 1. So then you would avoid like the foiling and all that, but the summation formulas start at 1. So therefore, that's why we would want to use this where we could make it be a 1, and not take it away from being a 1. Which, for those of you that are gone, let me talk about those summation formulas then. So what we had then was this idea about the sigma and just expanding out and being able to add up the value, okay? And why do we use a sigma? Because we're adding up rectangle areas. We're adding up 4 or 10 or 100 rectangle areas. We want a compact way to write that. So the sigma notation is going to give us a way to write that in a compact way. That's why sigma notation is useful here. We're adding up things. We're adding up rectangle areas. So, a couple of just sigma formulas that you do not have to memorize. They're on page 357 in your book. These will be given to you on the quiz if we need them, and we will. So these will be given to you. You won't have to memorize them, but they're on page 357 in the book. All right? So what we did is, so this is a sigma of a constant, sigma of I squared, and sigma of I cubed. And here's how you can get that sum by following this little formula. So let's go ahead. Could we work out 21 or 23? Would that be helpful? And that'll get us through the sigma part of it. Then I want to go catch up to where we were yesterday. All right? And we can go from there. So on number 20, 21 or 23, does it matter? They're kind of the same. They actually are the same. The only difference is this has a 1 over n cubed out in here. That makes this one a little confusing because this n is not the same as this 15. In the formula, when we do the formulas, we'll use 15 for all the n's, but not this one. So let's just ignore that one for right now, because I'm not going to give you one like that in the quiz anyway. So let's do 21. So on 21, what we would want to do, and we did one like this yesterday, right? We did get to this. Okay, so on 21, what we would do is we would first FOIL this out. We get I squared minus 2I plus 1. And the I goes from 1 to 15. Okay, then we would split that into 3 sigmas. So that would be sigma I squared minus, then we'd pull the 2 out in front. That would be sigma I, and then plus sigma 1. Now, and each one of these sigmas would be from 1 to 15, right? Now, according to those formulas on page 357 that we were just showing, sigma I squared is n is 15 in this problem, times n plus 1 times 2n plus 1, all over 6. So that's that first sigma. Then we would have minus 2, and then we would have sigma I. Sigma I is n times n plus 1 divided by 2. And then the last one, sigma 1, sigma of a constant, is the constant times n, which in this case, again, n is 15. N is this number. Or no, I did that wrong. Yeah. Mixed up 23. What should I have been using? Sorry. So this should have been 20, 21, 41. Thank you. 20 and 21. And then this should be 1 times 20. Okay, what are you getting on that one? 2,471? Now you can check that, you can just type that in your calculator, but I just want you to understand that sigma, that you can split this apart, you can FOIL that out, split it apart, same thing on all of these, and you would have a sigma I squared, sigma I, sigma constant, sigma I cubed could be another one, and we have those formulas for how to do it. They're just shortcut formulas for doing a sum, a long sum, if the formula fits one of those. Okay, that's all they are. Okay, summation formulas for doing a sum. So that's if we were to generate this, you can think about it. Put a 1 in there, you get 0. Put a 2 in there, you get 1. Put a 3 in there, you get 2 squared is 4. So you'd have 0 plus 1 plus 4 plus 9 plus 16. Go all the way out to 20 in there. Add that up. That's the number it would add up to. That's what you're doing. All right. Now, when we go up to this part of the homework up here, we're not going to go through it yet, but now it gives you this. Now, this seems really strange to you since we got interrupted by the fire drill, I'm guessing, right? When you got to this part. It wasn't hard. It wasn't hard to do these, but how does it fit in with what we're doing, right? This says find the limit as n goes to infinity. Okay, and you got these things. Well, to be honest, we should be able to do that with limits. Okay, but I want to hold off on that thought just for a second. So let's come back to where we left off yesterday, which was right here. I believe this is where we were when we had to leave. Okay? So, everybody ready? Hang on. Okay? Here's where we started. We said we've got an integral, an area we want to find from 0 to pi. Okay? That's this area right here. We know we can find that area by the antiderivative. We went ahead and found it. It was 1/3 pi cubed, which came out to this decimal. So we know that's the area we're looking for. What we said is, okay, let's do an approximation of that. Let's do 4 right rectangles. So we found out the width was pi fourths. We wrote out the sum. Why did I write the sum this way?
We saw it as rectangles.
Yeah, I mean, when I told you 2 days ago, or I don't know how many days ago, when we first started writing out these rectangles, I said, I'm going to not make you do this for busy work. I'm going to make you write this out because we want to see patterns. This is the part I was talking about. Okay? So we've got to figure out the width is pi fourths. Okay? Keaton, I'm sorry, do you have a question on something? I feel like I'm going past something that you're still confused on.
Okay, for 21, I did something different than splitting them up. I did something weird that same answer. I don't know how.
Which could either be coincidence or it might be fine. What do you mean by something weird?
For 21, I plugged in 20 to the I, and so I did 19 squared instead of like 20 squared. And so I looked at it as 19, so I did 19 times 20 times 39 divided by 2.
Say that again. So you use the formula
Yeah,
for I squared,
I just used the 19.
but use 19.
I just did 20.
Here's why it worked. Okay, the first term of this sequence, I just said it here a second ago actually, but I didn't think about it in terms of this. Okay, let's put a 1 into here. Let's write this out. Put a 1 in there. What's the first term? What's the second term? You seeing why already? Put a 2 in there, you get 1. Put a 3 in there, you get 4. And you go all the way out to put a 20 in, you get 19 squared. Okay? That's 20 terms. What if you only added up 19 terms? Be the same because the first one's 0. So this sigma 1 to 20 is the same as this sigma 1 to, no. It would be the same as this one, 1 to 19. Because 1 to 19 would just give you 1 plus 4 plus 1. Okay, so back to your question earlier. You can't just rearrange this, go 0 to 19, and then use that 19 in the formula. Only because it's 1 to 19, because that first one's 0 is the only reason that works. So that was kind of a coincidence. Okay? That's right. So you'd have been golden. You'd have been golden. Well, again, the only reason I could tell there was something bothering you about something, and I thought, now you're going to miss out on this other stuff. So sometimes you got to get that straight before you go on. So that's fine. But it was bothering me that I could tell something was bothering you. All right. So here we go. So back to this. So we've got this area from 0 to pi. We know the area is pi cubed over 3. Okay, which came out to that decimal. We want to write this out in the long form. But now, for you guys that were gone yesterday, what did I do? I found out the width is pi fourths, so I'm going to do 4 subdivisions. Okay? So my first right rectangle will be at pi fourths, next one 2 pi fourths, next one 3 pi fourths, last one 4 pi fourths. And I write it that way because I'm going to write a sigma, so I want there to be a pattern. I don't want to simplify 4 pi fourths and 2 pi fourths because now, when I write the sigma, and guys, this is the big emphasis for today. What we want to be able to do at the end of today is I give you this integral and you write this sigma right here. We've got to be able to do that, right? That's going to be a big part of the next quiz. Here's an integral. What's the sigma that goes with that integral? for 4 rectangles or 10 rectangles or 100 rectangles or whatever. Okay? So this is the process we're going through. Now, so we get our width, we write out our 4 rectangles. Now we look for the pattern. So I write my sigma. We got 1, 2, 3, 4 of them, so that's why my sigma goes 1 to 4. Notice those numbers there don't have anything to do with these numbers here. Right? This is 0 to pi, that's the total width. This is how many rectangles I got, 1 to 4. All right, now I look at my things here and I say, okay, every one of these has an F, every one of these has a parenthesis, every one has a 4 on the bottom, every one has a pi 4. So the only thing changing is this top number. It goes 1 pi, 2 pi, 3 pi, 4 pi. Well, that's what I's doing, going 1, then 2, then 3, then 4, right? So I put an I with the pi on that top number, on the top of the fraction, and that generates that sequence for me. So when I's a 1, I'll have pi force in here. When I's a 2, I'll have 2 pi force. When I's a 3, I'll have 3 pi force, and so forth. Okay? That's what we call being written in F notation. We want to take it out of the F notation by taking I pi force and plugging it in for x. Because that's what we do. If we have f of 2, we put a 2 in for x. F of a, we put an a in for x. F of I pi force, we put an I pi force in for x. So we put that in for x, that's squared, we get that. Okay? Now, today, on our homework for Monday, we will actually stop right there. We'll be good stopping right there. Okay? But yesterday we had another goal in mind, and so for this part of today, we want to go a little farther with this. So, I'm going to go ahead and simplify this out. So I square that, I get pi squared, I squared, 16. Take the pi times pi squared, that's pi cubed, I squared, I get 16 times 4 is 64. So I simplify that out. Now I come over here. The pi cubed and the 64 is a constant, so I'm going to pull that out in front. So here's my pi cubed and my 64 out in front. That leaves me just an I squared, right? That leaves me sigma I squared. Oh, we got a formula for that. N plus 1, 2n plus 1. So our n is 4. So 4, 5, 9 over 6. We work that out, we get 30. 30 pi cubed over 64. Now, I can't remember. I think that's when the bell rang. Okay, on your calculator, somebody take 30 pi cubed over 64 for me, please. And give me that as a decimal. 30 pi cubed over 64. Really?
Oh, I don't know.
What? Say what is it?
14.5.
Oh, good.
That's nice.
Okay, it's that right there, right? So we typed this in the long way yesterday. Remember that? And then we got this. And again, what is this number? I mean, it's so easy to get lost in the weeds here because the weeds are really tall in this. What is this number?
The rectangles.
How many?
4 rectangles.
What rectangles? Right rectangles, yes. This number is the area of 4 right rectangles under this curve. Okay, now, so this, when we worked all this sigma stuff out, all these crazy formulas, we got the same thing. We got the area of the 4 right rectangles. Okay, now, this is a part we're going to scoot through pretty fast. If 4 rectangles are good, 100 would be better. So let's do 100 right rectangles. Okay, I've gotten us to here. Now, I'm not saying you don't need to even write it down, to be honest with you. Don't worry about it. But look what would happen. How wide would it be? Well, if we go from 0 to pi, we're going to divide up into 100. What's the width? Pi over 100. So the first right rectangle would be at pi 100ths, then 2 pi 100ths, then 3 pi 100ths, all the way to 100 pi 100ths would be the last one, which is at pi, right? 0 to pi. Okay? So there it is. We can see the pattern. We got F, parentheses, we got pi 100ths of width, we got 1 pi, 2 pi, 3 pi, all the way to 100 pi. That's the I pi. Sigma goes from 1 to 100. Right? Now let's take it out of the F notation. Let's take our I pi over 100, plug it into the function, which was x squared. We got this. Now, help me with this. We'll do it quickly. So I could do all the same stuff I just did a minute ago. I could square that. And so that's going to be an I pi, it's going to be an I squared pi cubed, right? And the bottom's going to be 100 squared times 100. What's that? 2, 4, 6 zeros? And that's sigma 1 to 100. Now I can use my formula. I can take the pi cubed over a million out in front, and I got a what? I got a sigma I squared, right? Okay, so what's a sigma I squared? That is an n, which is 100, times n plus 1, which is 101, times 2n plus 1, which is 201, all over 6. Okay, so do that for me. Take pi cubed divided by a million, and then take it times 100, times 101, times 201, and then divide by 6. And do a control enter kind of thing so we can get a decimal. Because we certainly remember, as you guys are typing that, remember yesterday we did f of pi fourths times pi fourths and f of 2. Remember we typed that all out? We defined f of x to be x squared, right? We certainly don't want to do that with 100 rectangles. We're not going to type that out. This is why we need sigma notation to do something like this. This will add up the 100 rectangles for us really fast. What are you getting? Give me a decimal. Is that good? What is that number again? The area of 100 right rectangles. What was our actual area? 10.335. So that's pretty good. That's pretty good. A little big, and we'd expect right rectangles to be a little big. Right rectangles would be a little bit over on that particular graph. Okay, well, wow. If 100 rectangles were good,
That's what I mean.
or let's just, how about this? Yeah, 1,000 be good, million be good, 10 million be good. Let's get really good. Let's be exact.
Oh, yeah.
Infinite.
We learned to add infinity last
So here's what we want to do. Okay, yes. So, okay, you don't have to write this part down yet either. Okay? But here's what's going to happen. Right? We're going from 0 to pi. We're going to have n rectangles. Right? I can't put infinity in there. It's not a number. So we'll let n go to infinity. Right? So we're going to use n rectangles. So 0 to pi, split it up into n subdivisions. What's the width? Pi over n, right? Pi minus 0 divided by n. So the width is going to be pi over n, pi over n, pi over n. Here's 0 where I'm starting. One width over will be 1 over n. And then, no, 1 pi over n, right? Because we're pi over n. I'm sorry, the width is pi over n. So 1 pi over n, 2 pi over n, 3 pi over n, 4 pi over n, all the way to n pi over n, which again would just be a pi, which is what we want, because that's the far right edge. So 1 pi over n, 2 pi over n, so forth. So again, we can see inside here, I pi over n, plug that back in, we got this. Okay? So let's do the same thing we were just doing a minute ago. Let's square that, times that, that'd be pi cubed, I squared, n cubed. So I pull that out in front, I got my sigma I squared. So I got my pi cubed over n cubed, which is this, and I got my formula for sigma I squared from 1 to n, right? But I have no number to plug in like we plugged in the 100 before and then 4 before. I just got this. All right, now, here's where this comes in. Limit as n goes to infinity. What I need to do now is the limit of this as n goes to infinity, correct? Does that look familiar? Okay, you see now where these problems came from in homework. Okay, it's been so much better if we would have had to got to do this yesterday, but maybe not, maybe not. But you see what I mean? Look at those right there. That's sigma I cubed right there. Right, that's the sigma I cubed formula. Okay, right there. There's sigma I squared formula right there. Right. So these problems here, all they wanted you to do was do n goes to infinity. So in these problems, they were just saying, hey, just do that one piece of this whole process we're talking about here. Okay, so right now I'm going to do the limit as n goes to infinity. Now, how do you do limit as n goes to infinity? What's one way to do limit as n goes to infinity? We had L'Hopital's rule, but that was derivatives, and that's a mess, so I'm not sure about that.
Just pay attention to the largest
Largest power, high powers dominate. High powers dominate, which looks perfect here because this is a problem with powers in it. So all I care about here is if I multiplied this out, what would be the highest power? Yeah,
You need to have
the highest power would be cube, but there'd be a 2 on it, right? If I was to multiply it all out, which I don't even have to, I would have a 2n cubed and then a bunch of other stuff that I don't care about. And then there'd also be this pi cube sitting up there. This is getting good. You can see what's happening maybe. Maybe you see it already. Look what happens here. We already have a 6 down here, right? I have a 6n cubed. Now what happened? N's cancel. What do we get?
Oh my
Does that look familiar?
No,
It doesn't?
no, it does.
I'm gonna start throwing things.
It was the exact area. Well, right. I mean, it should be, right? How many rectangles did we just add up here? An infinite number. We just added up, by doing this, we just added up an infinite number of rectangles. We use this summation formula to give us that sum. And by doing the limit as n went to infinity, we just added up an infinite number of rectangles under that curve. It gave us this, and we already know by antiderivative that this area is supposed to come out to be that, and sure enough there. I'll tell you what, it has been. I'll tell you what, between getting to do this yesterday, getting to go to Bellevue East and win and qualify for state, and then come back and get to do this again today. Pretty good 24 hours, I must say.
Not even burning in the fire yesterday.
I know, yes. I mean, yes, if we all were safe from the fire. I mean, you throw all those things together, and it's very exciting time.
What
Now,
happened yesterday?
Um,
No, but I mean, what happened? What the fire?
we still don't know. I think there's still some kind of a short or something going on in the system that they can't find that's making it do that. So anyway, let's keep going in case it goes on. All right. So now, whoops. So now, here's what this leads us to. Okay, is we now have a way that we could write. Now this you can write down. Now we could write our formal definition of an integral. It's not really useful from a practical, solve a problem standpoint. It's kind of like the definition of the derivative. The definition of the derivative, but maybe even less so, the definition of derivative was limit as h approaches 0, f of x plus h minus f of x all over h, which really just said 2 points become 1. How do you do slope of a point? You pick 2 points that get really close together, infinitely close together. Okay? And that's where the limit became involved. Well, this is along those same lines. How do you find the area under a curve? Well, you don't. You find areas of rectangles. And you add them up, and you do enough rectangles that you get closer and closer to the actual area. How many rectangles? Infinite number of rectangles. So it's a very same process then, how we found the derivative to how we find the integral. So here's how it would look written out. Then is like this. The integral, the area under the curve f of x from a to b is simply this big mess of notation, but now that we've went through it and we've kind of built ourselves up to it step by step, hopefully this makes sense. This is rectangle areas, heights, widths. The sigma does what? Adds them up, and then the limit part means we have an infinite number of them. Matter of fact, if you had to describe, like say, I don't know, on a quiz question, if you had to describe why this would be the area of why would this here be the area under the curve, I would just break it up into those parts. I mean, I would say, well, this represents the width of a rectangle. This represents the height of a rectangle. When you multiply those two together, you get area of a rectangle. When you take the sigma, that adds them up. And then when you do this, this means you have an infinite number of rectangles. I mean, so that, when you put that all together, that pretty much tells you why that gives you the area under the curve, because it adds up an infinite number of rectangle areas. Why are those rectangle areas? Because that's the height of the rectangle and that's the width of the rectangle, and you multiply those two and you get the area of the rectangle. And so this, in a nutshell, is saying add up an infinite number of rectangle areas. That's what that is saying. Add up an infinite number of rectangle areas, and you will get the exact area. And we know it because we just proved it. We just saw it happen, okay, for that particular problem. All right. Now, we want some practice on that idea of here's an integral, write out the rectangles, turn it into a sigma. That's the mechanical piece we really need to work on today, on getting that done. But this is kind of the big idea of what that is. Now, there's another thing hidden in here that I think is really kind of important. Do you see, hopefully there's a little new added meaning of the dx here now. I mean, look at this compared to that. You see what I mean? The delta x is kind of in the spot where the dx is. And let's think about delta x a minute. If you have an infinite number of rectangles, I mean, truly, if you could have an infinite number of rectangles, what would the width be? It'd be nothing, right? If you could truly have an infinite number of rectangles, the width would be nothing. So on this side, that's what we're saying. We have an infinite number of rectangles, and guess what? This basically is nothing. For us, this is just, well, with respect to x. It's just hanging out there, means with respect to x, because it really has no value once you go to an infinite number of rectangles, okay? But we're going to think of it as width, because it can be really helpful in some story problems. Remember the one we did the other day about gallons per hour? We were talking about that one. We had like W prime in here or something like that. I don't remember what the V prime, whatever. This was gallons per hour. Here's how we're going to do this. When we work some story problems, we're going to look at our integral, and we're going to look at it this way. We're going to say, well, okay, this function is gallons per hour, and the dx would be hours, because, right, that would be your x units, which would be the time, the hours. And what's gallons per hour times hour? Gallons, because that would be your height and your width in your rectangle. Now, we know that because of antiderivative. We just said, well, if you have gallons per hour, you do the antiderivative. That's gallons. Okay, but this kind of tells you why it is. Gallons per hour times hours would give you gallons. Okay, and so we'll use that to our advantage to help us set up some story problems where we will actually think of the dx as kind of that width piece to this. Okay, at least from a unit perspective. And I think that's can be helpful. Okay, all right. So those were kind of the things I wanted you to see from that. Now let's go back to the homework part. So then hopefully this becomes pretty easy, because if you take one like number 29, do we have to do 29? If you take one like 29, if you were to distribute that all out, on the top you'd have 18n squared, right? And some stuff that you wouldn't care about. You just care about high powers dominant. And on the bottom here you have what? 2n squared, right? N squared cancel. You get 9. That's literally all you really had to do on that section. It was just n, that kind of thing. But I wanted you to see where these problems came from. They came from that whole sigma thing we were just doing. All right, and now when you get down here to 31 and 33, now you combine what we did in 21 with what we just did in those other problems. So all you would do is you would take on 31 here, and we're not going to take time to go through it, but on 31 you would just take what we did, where we did that whole split it apart thing. You'd make this I squared minus 2i plus 1. You just pull the 1 over n cubed out in front here. Okay? And now you would have your sigma. So you'd have a sigma I squared. Well, that would be n times 2n plus 1. Oops, I forgot. And n plus 1 over 6. And then minus 2. And then you'd have your sigma I. What was that? N plus 1 and 2. And then you'd have plus sigma 1, which would be just 1 times n. We'd have all that, and then we would have 1 over n cubed. Okay? So we would do just like you did on problem 21 and 23, 19, which was split this apart, do your sigma formulas. We have the 1 over n cubed out in front. Now do n goes to infinity. So now you're doing just like we just did on that problem up above. So n goes to infinity, all we care about here is what? High power. So here you'd have a 2n cubed. Here you'd have an n squared, so I didn't care about it. Here you'd have an n, I didn't care about it. So all I really care about here is I got a 1n cubed times a 2n cubed over 6. N cubes cancel, I get 1/3. So all I care about there is all I get for the answer is a 1/3. Okay? But again, what would this be representing? This is probably representing some infinite number of rectangles, some piece of area. There's some integral that this came from. And that's what we're going to work on over the next several days. We're looking at a quiz on Wednesday. And over the next several days, what we're going to be doing is how can we take an integral and turn it into a sigma that represents all the rectangles added up? And how can we take a sigma that represents all the rectangles added up and turn it into the integral that created it? Kind of just going back and forth between those. That's what we're looking at. Okay. So, feel like I'm missing something. Yes, there it is right there. Turn to page 355 real quick. Okay, let me ask this question. So I'll do this a little differently. If I give you this integral right here and ask you to write out an L3 approximation, could you do it? Just look at it, take a minute, and write out an L3, a sum, okay? Write out 3 left rectangles for that problem. Now, is there any, go ahead and finish here if you're on to something. Is there anything in there that is causing you difficulty, though, or that you'd have a question about, or you're missing? Are you missing anything? Who would say no? I'm not missing anything. I can write out 3 left rectangles. Okay, wait a minute. It can't be both, can it? On the one hand, I said, are you missing anything? Nobody said anything. And then I said, okay, well, who's not missed anything? And then nobody said anything either. No, I'm afraid to be wrong. What, do I make fun of you when you're wrong? I don't think I do.
You could write it out, but you couldn't solve it.
Okay, so you go ahead, Brandon. Tell me what you would write out.
You would have f of 2 times 1 plus f of 3 times 1 plus f of 4.
That could not be any more perfect. Very good job. That is awesome. Now, you said you can't work it out. Why? You don't know what f is, right? Now, we have, up to this point, and yesterday's homework, remember all the pretty pictures and stuff, and we graphed our rectangles first, then we did this. But my point on this problem is, do we really need the graph? No, to do a left rectangle approximation or right or midpoint or trapezoid, you do not need to know what the function is, what the graph looks like, any of that stuff. You don't need it. Whatever this function is, and maybe it's some equation, but you don't know what the graph looks like, and you don't have a calculator. Well, who cares for right now? This is all you need to know. Now, could a graph help you a little bit? Now, you'll see what I like to do on these problems. I don't really care what the graph is, but what I will do oftentimes is I will make myself at least the x-axis, and I will say, okay, this is going to be an integral from 2 to 5, because I think pictures can be helpful. What's the other part that I need here? The width, right? So 5 minus 2, and I have, 5 minus 2, and I have 3 sections, 3 subdivisions, so b minus a divided by n, so 3 divided by 3 is 1. So that's an important piece to get. So once I know that, on my graph, I can go 3, and then I can go 4, and then I can go 5. And if you wanted to, I don't even know what this function is, so who cares? But I could say to myself, all right, my first left edge is going to be there, right? And that's going to be, you know, and I don't know what the function is, but this at least helps me see it. All right, that's f of 2, and then times it, and then f of 3 and f4. And of course, your last one, you don't use the 5, right, when it's a left. If this was a right, what would you have had? 3, 4, and 5. Okay, now I want you to look at problem number 25 in your book. Okay? What's the function? It's just a table of data, right? It's just a table. Who cares? If the function's an equation, it's a graph, it's a table of data, it doesn't matter. It doesn't matter. So you want to do an L3 approximation, boom, here we go. And so all you need now is to look at the table. What's f of 2? 0.21, 0.28, 0.36. We don't know what the function did in between there, but we don't care. Boom, 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 add those up, and you got your L3 approximation, right? So when we do an L3 or an R4 or whatever to an integral, right? Function could be a table, a graph, all those things. All right. Take out your 2012 free response packet and look at problem number 1. Look at part C. Remember when we did that a few days ago? We couldn't do it, right? You guys were like, Riemann, what the heck? Right? Now we know. Now, let's talk about a couple parts. So we're going to go ahead and do this one real quick. It says for 0 to 20, the average temperature of the water is this. Now, I wrote it differently. This is how we remember average value of a function, right? That's a little formula we said we got to know. Average value of a function. The average value of the W function is this integral divided by 20, b minus a. Now, sometimes they'll write the 1/20th out in front when they do it. Okay, so that's what they did. But they just told you. You didn't have to memorize it this time. They just told you that was it. Use a left Riemann sum to approximate that. Now, the Riemann sum is really only approximating the top, right? The 20 is just down there. The Riemann sum is approximating the integral. Okay? So we want to do a left Riemann sum. Now again, who cares that it's a table, but we can do a Riemann sum. Now we're going from 0 to 20. We're going from 0 to 20, and we want to do 4 left rectangles. So what's the width? Logan, what's that? Why? Okay, so here I just said, what's the function? We don't care. Well, yeah, we kind of care. We have to kind of care. Because when it's a table of value, we only have certain values. If we have a graph, if we have an equation, we can plug anything we want in. So we can do equal intervals, and we can do it that way. When you have a table, you do have to work with what's there. So you do have to change that a little bit. So this is another one of the reasons, though, that I was wanting you to write out your height, width, height, width, height, width, getting a sense of that, because let's think about it. Where is the first left rectangle going to be? Let's use F notation. F of 0 times, the first one is going to be 4y. What's the next one? 4 times 5. Next one, F of 9 times 6. And the last one, F of times 5. Because it's going to be 5y to the next width. And we don't use the 20. On the left, we don't use that last one. On the right, we don't use the first one. So that's what you would have written out for that one. And then you would have said, you get that answer. We won't do it just this minute, but we would take those numbers, that times 4, that times 5, that times 6, and that one times 5. And we'd add those up. We divide by 20, and we would get the average temperature based on the information that we have. Now that's a left approximation to the average temperature. Then they ask one other question. Does this approximation overestimate or underestimate the average temperature? Why?
Because since it's increasing and it's a left rectangle, then there's space underneath.
And we're going to spend a lot of time in chapter 6 talking about this more. But that's exactly right. Since this function is increasing, left rectangles are going to be underneath. So that is whatever answer you got when you work all that out, that is going to be an under approximation of the actual average temperature. Okay, so we're getting there, bits and pieces we're picking up as we go along here. All right, so let's do basically some of your homework problems now. Let's go ahead and get started with that. And we may have to spend the rest of the time working together on it. We'll see how it goes. We're going to get into section 5.7 now in the book. Now in section 5.7, this is where it gets into the sigma notation. So these first sigma problems are just like the LH packet. Just expand out the sigma, try to write a sigma formula. So it's good practice. I don't want to skim over that as too easy or unimportant, but it's, if you have questions on some of that, be sure and let me know. And then, but the real important ones here for us, 13, 14, 19, 20, and 23. Now, something that will come up to help us. Oh, I'm sorry. So, something that will come up here that will help us. Let's investigate something here just real quick. We were just talking about right and left and kind of the differences between them. Yesterday, let's do this. This would be a good way to do it. Yesterday we had, you don't need to write this down, but yesterday we had a right sum that looked like this. Right? What would the left sum have looked like on that one? Remember, it was the integral went from 0 to pi. F of 0 times pi force plus f of pi force times pi force plus dot, dot, dot. And the last one, 3 pi force. Correct? Okay? And so we wrote the sigma for this one, and it went 1 to 4. Like that. And then what was in here? Right? So it was that. Now, what would the left one have looked like then? What now? Okay, right. I didn't say you had to do the same formula. Logan, what were you going to say? And use the same formula. So what now keep in mind something we said earlier today. You can rearrange sigmas to start anywhere you want, right? So there's not just one answer here, right? So we could do I pi over 4 and have this go, and that would do it, wouldn't it? And that's a pretty good lesson, and that actually is always true. Rights, remember I told you we like to use the rights because those start with 1 with their sigma, and because, you know, here's your left edge and your first right edge is 1 over. And so you go 1, 2, 3, and you go all the way to the end. And it just seems like a natural progression. Lefts, you start on the left edge and you stop 1 short. But if you just make that little adjustment in your sigma, keep the same exact formula, then you'll have your left. Now I say that because we're going to do number 13, which is several examples using right rectangles. And then 14 says do the same thing now, but with left. Well, pretty easy, right, if you understand this. Now we could have started this at 1 and made an adjustment and made our formula different, and that would have been okay. If you want to do that, that's fine. But typically in these problems, if you see an I equals 0, you're thinking left rectangle. If you see an I equals 1 to start, you're thinking probably right or maybe midpoint. Those usually start with 1. Okay? So that's just something to consider when you're thinking about rights versus lefts. All right? So, when we go back to this right here, right, this is 100 right rectangles. If we wanted this to be 100 left rectangles, 0 to 99. Because then our last one would have been 99 pi over 100. And our first one would have been 0 pi over 100, or 0. And that's exactly right. Okay, so what I'd like to do now is erase that and do number 13 with you. And let's go through. If I'm going too slow, you can just leave me in the dust and keep going. Okay? Now it's got 4 parts. This is on page 362. Okay? Now, it's got a definite integral, and it wants us to write the sigma for 10 right rectangles. Then part B wants us to do 5 right rectangles. Then it wants us to do 20 rectangles, and then it wants us to do 50 rectangles. Now, you're going to notice a pattern. Once you do one, the next one might be easy, whatever, okay? But here's the process that you should go through with this. Step 1, what? We're doing 10 right rectangles right now. Delta x. So 10 minus 0 divided by 10 equals 1. Always simple when the width is 1. Always simpler. Okay? Next step. Now, this is where I will a lot of times, because I just think it's helpful, I'll make myself like an XY axis. I'll look at my integral. I don't care that the function is x squared. I don't care what it is. But I want to know my subdivision. So now I'm going to go, okay, this is 1, then 2, then 3, then dot, 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 up to 10. Because the width is 1. Okay? So I like to do that. So where's my first right? F of 1 times 1. F of 2 times 2. I think writing this out is important because sigmas, I think, are always easier to write if, that's not right, is it?
No.
Darn it, I do that and I keep talking and you guys, I've lost you because I'm screwing up here, my fault. That's 1, right, good catch, that's the width. But I think sigmas are always easier to write if you see a pattern, and a pattern's always easier to see if you've got it written out. If there are parts of this you can shortcut, I'm okay with that. Okay, I'm okay with that. It's up to you what your level of understanding is. All right, so now I'm looking for the pattern. So my sigma I is going to go from, well, who cares? We'll get that in a minute. I got F, I got 1, and what do I got? Inside is a 1, then a 2, then a 3, then a 4, all the way to 10. So inside is going to be, that's the I. I mean, it was more complicated before. We had I pi over 100, but whatever. And this one is just pretty simple. It's 1, then 2, then 3. That's I. And I is going to go from 1 to 10. I can't emphasize enough, though, that this 0 to 10 here is totally separate from this 1 to 10. They don't have anything to do with each other. Right? This 1 to 10 means what? 10 rectangles. This 0 to 10 means we're doing the area from 0 to 10. Two different things. All right, last step then is to take it out of F notation, which means plug it back in for the x. So we're going to take the I, we're going to plug it back in for the x, so that's I squared times 1. Do you have to put the 1? Maybe not, but I like the fact that it means height and width. Height and width. So the 1 doesn't have to be there, but okay? But you don't have to go work it out from there. On these problems, we're done. We just do the sigma. Okay? Now, part B. Part B wanted 5 rights. Right? Now, I don't know how much of this I need to redo again. I mean, parts of it I certainly do. What's the width? The width this time is going to be 2. So on my little picture, I like to just have that. Oh, it just, I'm not sure why. I just think that it's easy for me to visualize that one. So that's 2. So my first right is going to be at 2. So we're looking at f of 2 times 2. F of 4 times 2. Write more if you want. F of 6 times 2 if you need another one. Plus dot, dot, dot. Last one's going to be at 10 times 2. Okay, the width is 2. Right rectangle at 2, at 4, at 6, those are my right endpoints. To get my heights of my right rectangle. So now what? This is F, parentheses, I got a 2 out here. How do I generate that sequence? 2, 4, 6. Isn't that 2i? Yeah, so it changes a little bit there. It'll be 2i. Because when I is going to go from the 5. And now let's take it out of the F notation, and so we'd have sigma. So we take 2i and plug it in for x. So that would be 2i squared times 2. Right? We're going to take the 2i, f of 2i means take 2i, plug it in for the x. There we go. So this sigma came from this integral, but so did the other sigma we had. It's just that one of them, again, this sigma represents what? Sum of how many? What type of rectangle? Right rectangles. This sigma represents the sum of 5 right rectangle areas. Okay? The other one was 10 right rectangle areas. Part C. Supposed to do an R20. Supposed to do an R20. What do we got? The width would be 1/2. Going from 0 to 10. 1/2. What comes next? Ah, good. 2 halves. 3 halves. 4 halves, all the way to 20 halves. 20 halves, right? Not 40, not because I'm going by 20, I'm going to 10. I'm ending at 10, right? The last one will be 20 halves. Because I'm going by halves, I'm going to do 20 of them, but that's 20 halves. 1/2, 2 halves, 3 halves, 4 halves, 5 halves. It's easier if you write it that way. So when I expand this out, that's how I'm going to write it. My first right will be at 1/2 times 1/2. And then 2 halves times 1/2. I usually write out 2, maybe 3 if I think I need it to see the pattern. Dot, dot, dot. Last one is at 20 halves. Could you have written that as a 10? I don't care. That's fine. You could have written this as a 1. This is a 1.5. You could have used your width as a decimal, 0.5 if you want. I don't think it's as easy to see the pattern. 0.5, 1, 1.5, 2, 2.5. I don't know if that's as easy to see. Maybe it is. It might be for you. I think the decimals work fine. Okay? And I'd be perfectly fine if you had that. So what do we got? We got F, we got parentheses, we got a half. Every one of them has that. Every one of them's got a 2 on the bottom. The only thing difference is top number. 1, 2, 3. What's that going to be? That's the I. And I is going to go in my sigma from 1 to 20. And then the final step, take it out of the F notation, and you got it. I'll let you go from there. So the next one is 50. Now that one, I'll bet you can learn a lot from this. I'll bet you don't have to write out as much stuff on that one. I'll bet you can kind of tell what's going to happen with, now that you're into the fractional type ones, what will be there. And then one last comment. When you get to 14 and you need to do a left rectangle, what do you got? 0 to 19. You take this same formula, but you go 0 to 19, and then you'll have left rectangles, because the first one will start at 0, and then here, and then here, and it'll end at 19 halves, which is one short of the right edge, which is what left rectangles do. All right, 19 and 20 are very much the same. 23 is a midpoint, so that'll make you think a little bit. Okay, that'll make you think a little bit on that. You may.